Hi guys, today I'm going to talk to you about quantum equations. Let's talk about the wave equation first. The wave equation is the speed of the wave equals the wavelength times frequency. Now the speed of the wave is c, the speed of light. Notice that this is 3.0 times 10 to the 8 meters per second. The wavelength is measured in lambda, and this is a Greek letter. Lambda equals wavelength, and wavelength, you guys, is measured in meters. Okay, so frequency is represented by the Greek letter nu, and this is the Greek letter nu, and frequency is usually measured in hertz, or we can say that it is cycles per second. Okay, so this is another way we can write it. 3 different ways of writing it. Okay, so let's do the first equation. It says, what is the frequency if the wavelength equals 4.09 times 10 to the negative 7 meters? So this is what's given to us, and this is what we need to find. Okay, we're going to use this equation right here. So C equals wavelength times frequency. Since we're trying to solve for frequency, we're going to divide by wavelength on both sides, and now we are left with I'm going to put it right here, with wavelength, frequency is equal to the speed of light divided by wavelength. Okay, so we're going to go ahead and plug our numbers into this equation. So the speed of light, 3.0 times 10 to the 8 meters per second, divided by wavelength, that is 4.09 times 10 to the negative 7 meters. Okay, our meters will cancel and we will be left with seconds, and that's fine because remember, frequency is cycles per second, so we're left with seconds. You're going to put this into your calculator. Okay, and when you put it into your calculator, don't forget that you're using the second EE sign. Okay, and that's going to be 3.08. You're going to use that second E divided by 4.09 second, and you're going to use that comma sign. So you're going to use that comma right above the 7 to get your exponent, which is a negative 7. And when you do, you get this as your answer. This is a long number. But realize, you guys, when we're looking at this, you do not use the speed of light as one of your sig figs, because speed of light is a constant. You never use constants. You only use the values that are given to you, experimental values. So this is 3 figs, so our answer is also going to have 3 figs. So our answer is going to be 7.33 times 10 to the 14th. And this is cycles per second, so I'm going to write hertz over here. Okay. Moving on to the next one. What is the wavelength if the frequency, which is given to us, equals 7.8 times 10 to the 6th hertz? So wavelength is what we are trying to find. Once again, we're going to use the wave equation. So the speed of light equals wavelength times frequency. I'm trying to solve for a wavelength, so this time I'm going to divide by frequency. Okay, so my equation will be wavelength is now equal to speed of light divided by frequency. So I'm going to put it right here. Start off with my constant speed of light, which is 3.0 times 10 to the 8 meters per second. And then I'm going to divide by my frequency that I'm given, which is 7.8 times 10 to the 6th hertz. You can put hertz, or you know that hertz is cycles per second, so we can actually write cycles per second. So I'm going to write that 1 over s, and now my s is going to cancel out, and I'm going to be left with meters. So when I put this into my calculator, again, when I put this into my calculator, oh, I think you can see it better there. It is 3.0 divided by to the 8th power, 3.0 times 10 to the 8th, divided by our hertz, which is 7.8. and I'm going to press second, that comma sign that gives me the exponent 6, and that is my answer, 38. So my answer is 38, and go back. Okay, so your answer is 38, and remember it's 38 because you don't count the significant figures on your constant, which is the speed of light, but you do look at your given, and your given has 1, 2 significant digits, so your answer is going to have 2, and your unit is meters. Okay. Moving on to the next one. So if a radio station broadcasts at 94.7 megahertz, what is the wavelength? So realize over here that we're dealing with a prefix, and so we want to first put this in, use the SI base for it. So we're going to go ahead and do the conversions first before we put it into the equation. So we have 94.7 megahertz. Okay, since you don't want your answer in megahertz, and you guys keep in mind we are doing dimensional analysis for this, since we don't want our units to be in megahertz, I'm going to put 1 megahertz down here, and I'm going to put hertz, the unit that I want, up here. And we have 1 times 10 to the 6th hertz. Okay, now you're going to put this into your calculator. Okay, so 94.7 times 1 to the 6th power. And that should give us quite a big number right there. Okay, so we can always put that number in scientific notation. Remember to cancel out the units. We are left with hertz. Okay, so I'm going to go ahead and put it right here. That is 9.47 times 10 to the 7th hertz. Okay, now that we have this, we're going to go ahead and use our equation, and we're going to solve this time. Realize, you guys, this is what's given to us, and we are solving for wavelength. So we're going to use the speed of light equation that we had earlier, the speed of light, and we're going to solve for wavelength. So C equals lambda over wavelength. If you're solving for wavelength, divide by frequency on both sides, and you are left with lambda equals speed of light divided by frequency. So go ahead and put that in there. 3.0 times 10 to the 8 meters per second divided by your frequency, and this is the frequency that we got. We converted it. So in this case it'd be 9.47 times 10 to the 7th to the hertz. And remember, if you don't feel comfortable with hertz, you can always put cycles per second. It is the exact same thing, but I'm going to go ahead and leave it this time and cancel out my seconds, and I am left with wavelength. So once again, I'm going to put this inside my calculator. So it's 3.0 to the 8th power divided by 9.47 to the 7th power. Okay, and I get this for my answer. I get 3.1. Now I have 3 significant digits right here. Remember, my original answer had 1, 2, 3. So I'm going to have 3 significant digits. So it'd be 3.1, and this 6 right here. And the 6 right here will be rounded up because of the 7. So it's going to be 3.17 meters that I'm going to have as my answer. Okay. The last one right here, you guys, is what is the frequency of the wavelength when it's 780 nanometers. This is what's given to you, and I want to find the frequency. Okay, so again, because we are given the prefix rather than the base, we're going to first convert this 780 nanometers. So 780 nanometers, and we're going to use dimensional analysis for it. Since I don't want my answer to be in nanometers, I'm going to put 1 nanometer right here. And I put meters up here. 1 times 10 to the 9th, and it's negative 9th power that I have. Okay. Okay, so nanometers will cancel out, and I'll be left with meters. So let's go ahead and put that in our calculator. Clear it. 780 divided by, not divided, multiplied by 1 to the negative 9 powers. Make sure you put that negative sign there, okay? And this is what I get. So I'm going to go ahead and put this in my calculator on my paper. So it is equal to 7.8 times 10 to the negative 7 meters. Okay? So now I'm going to go back and plug everything inside into my equation that I have, my wave equation. My wave equation is the speed of light, c equals wavelength times frequency. And since I want to solve for frequency, I'm going to divide by wavelength on both sides to cancel it. Now I've got my frequency is equal to the speed of light divided by wavelength. And so now I'm going to put it in my on my paper that the speed of light is 3.0 times 10 to the 8, and this is meters per second. And then I'm going to divide it by wavelength. And my wavelength is right here that I converted to meters. So this is a lot easier. One of the reasons why I do want to convert first is because I've got meters here and I've got meters already here. That makes it a lot easier to cancel. Nanometers and meters are two separate things. So now I can cancel my unit because it's the same units. So that's easy. And I can cancel, and I'm left with cycles per second, which is hertz. So I'm going to put this in my calculator. 3.0, which is the speed of light, to the 8th power divided by 7.8 to the 3.0. Keep pressing silly buttons. 7.8, and that is to the negative 7. Okay. All the more reason to always take it slow, right? Okay, so make sure you are calculating this correctly and putting it correctly in your calculator, but realize that this is 2 sig figs, so our answer is going to have 2 sig figs also. So it's going to be 3.8 times 10 to the 14th, and this is cycles per second, which is what hertz is. Okay, that is what hertz is. Okay, so this concludes our talk on the wave equation. So let's go ahead and look at our at Planck's equation. So further down. So looking at Planck's equation, now this is Planck's equation, and this is energy, and this is of a photon. So when I say that this is the energy of a photon, I'm saying that this is the energy of a single photon, just one, okay? So we're already given energy is equal to h. Now h is Planck's constant, so it's another constant that we have, okay, which is Planck's constant 6.626 times 10 to the negative 34th joules seconds, or joules times seconds. And then of course you know what frequency is. This is nu that we have. But what if you're not given frequency and you're given something like wavelength? Well, there's a way for you to work with this equation by substituting other variables into it. Okay, so let's do that. Using both of these equations right here, we have the speed of light, which is our wave equation, is equal to lambda times our frequency nu, and you're solving for wavelength for frequency, so divide by wavelength on both sides, and now you are left with nu is equal to speed of light divided by wavelength. Okay, well, this value can be substituted for the value for v. So if you have E right here, Planck's constant times frequency, now you can substitute this entire value right here. Okay, so you can substitute it. And so that'll become E is equal to h, and I'm going to substitute speed of light divided by a wavelength. So that's my equation right there. I can write this many ways. Another way that I can write it is E is equal to hc over wavelength. Okay. I can use simple algebra skills that you learned in Algebra 1, and I can switch the two equations around. So if I do, then I would get wavelength is equal to Planck's constant times the speed of light divided by E, which is energy. Okay, So from this equation and the wave equation, you can get two other equations right here. Okay, so moving on, let's go to our next bit of problems here. So the next problems we have, we have what is the energy of the frequency right here. Frequency, which is what's given to you, and energy is what we want to find. Frequency equals 6.02 times 10 to the 20th hertz. Okay, so we're going to start off with energy. E equals h times frequency, which is new. And we need to solve for energy, so we don't need to manipulate the equation. And Planck's constant. Remember Planck's constant? You guys don't have to memorize the Planck's constant number nor the speed of light. These are constants. So never really put brain energy into memorizing anything that's a constant. So 6.626 times 10 to the negative 34, okay, joules second. You're going to use this and you're going to multiply it by the frequency, which is 6.32 times 10 to the 20th hertz. Realize, you guys, that hertz is cycles per second, so the hertz will cancel out and you'll be left with joules. And energy is measured in joules, so this is correct. Okay, so we're going to put this into our calculator, and in this case I have 6.626 to the negative 34 times 6.32 to the 20th, and I'm going to get a really tiny number, but it does make sense, the number here. Okay, so I'm going to put this in, 4.19 times 10 to the negative 13th joules. Okay, now keep in mind, you guys, that this is three significant figures because we're looking at what's given to us. This is three significant figures. Never use constants, and Planck's number is a constant that's given to us, so we don't use that for significant figures. Okay, now moving on. What is the frequency? Okay, so we're trying to find this. If the energy, this is what's given to us, okay, is equal to 6.96 times 10 to the negative 18 joules. So we've got energy is equal to Planck's constant times our frequency. We're trying to solve for frequency, so we're going to divide by Planck's constant on both sides, so we'll cancel that. And our equation will be frequency equals energy divided by Planck's constant. Okay, so we're going to start with energy, and this is the energy that is in one photon, so 6.96 times 10 to the negative 18th, this is what's given to us, divided by Planck's constant. And you do not need to memorize Planck's constant, you guys. You can always program it into your calculator. Planck's constant as well as the speed of light, 34 joules per second. Okay, so we're going to cancel this, our joules, and we're left with hertz, or cycles per second, which is what frequency is equal to. So we're going to go ahead and divide. Okay, so 6.96 negative 18 divided by 6.626, and our exponent is negative 34. I'm going to put it in there, and this is what we get. Realize that we're dealing with 1, 2, 3 significant digits, so we're going to be 1, 2, 3 significant digits, 1.05 times 10 to the 16th. And realize this is cycles per second, so it is hertz right here. Okay? Okay, so now moving on to our next problem. We have, what is the energy if the wavelength is 1.18 times 10 to the negative 8 meters? Okay, so this is our wavelength. This is what's given to us, and our energy is what we need to find. So now we're dealing with wavelength and energy. So we're going to go back here, and use our equation that we derived. So if you look over here, here is our equation that gives us energy and has wavelength. The question is, which of the two equations should we use? But look, it's asking for energy with wavelength. So we already have an equation where energy is equal to something with wavelength. So we're going to use this equation right here. So I'm going to copy it down. Energy is equal to Planck's constant times the speed of light divided by wavelength. And we should have Planck's constant 6.626 times 10 to the negative 34th joules times seconds. Okay? And multiply that with the speed of light, 3.0 times 10 to the 8 meters per second. And then you're going to divide. Divide by your wavelength, and this is 1.18 times 10 to the negative 8 meters. Okay? Okay, so let's put that in our calculator here. Okay. Is that a little bit better? Okay. Okay, so 6.626 is Planck's constant, negative 34, times 3.0, we're going to use to the 8th right here, divided by, we're going to divide the whole thing, divided by 1.18 to the negative 8. Okay, so we get our answer right here. And notice that our answer is going to have 3 significant figures, so it's going to be 1.68 times 10 to the negative 17. The answer is going to be 1.68 times 10 to the negative 17. And let's see, meters cancels, seconds cancels, and we're left with joules. Joules is the unit for energy, so we're right. So here's our answer, 1.68 times 10 to the negative 17th joules. Okay, and finally our last one, what is the wavelength if the energy is equal to this? So we have energy as our given, and our wavelength is right there. Okay, so again, we're talking about wavelength and energy. So we're going to go back and use one of the equations that we derived. So this time we are actually solving for a wavelength. So we're going to use the second equation. So wavelength is equal to Planck's constant times the speed of light divided by energy. So we have that wavelength and energy right here. Okay. So it is, our equation is wavelength is equal to Planck's constant times the speed of light divided by energy. Okay. We don't need to manipulate the equation in any way. So we're going to start off with Planck's constant 6.626 times 10 to the negative 34 joules times second, and then the speed of light is 3.0 times 10 to the 8 meters per second. And then we're going to divide by energy, and our energy in this case is 1.10 times 10 to the negative 16 kilojoules. So we've got kilojoules right here, and I really need to convert it to its base unit, which is joules right here. So what I'm going to do is I'm just going to do my dimensional analysis right here. I'm going to have, since I want to cancel out kilojoules, I'm going to put 1 kilojoules right here, and I'm going to put 1,000 joules. Okay, you can put 1,000 joules. If you don't want to put 1,000 joules, you can always put 1 times 10 to the 3rd joules. Okay, either way you guys will work. Okay, so either one will work. You can put this value right here, or you can put 1,000. Doesn't make a difference. So now let's cancel out our kilojoules. Kilojoules, our joules cancel out, our seconds cancel out, and we're left with meters. As should be, it's wavelength. Wavelength is measured in meters. So let's go ahead and put this into the calculator. Okay. If I can get it in there. Okay, so we have 6.626 second, negative 34, times the speed of light, and this is going to be 8, divided by, and I'm going to divide it by this value, 1.10. I'm going to put it in my calculator, second, so it's negative 16. And then again, I'm going to put divided by because I'm dividing again by 1,000. So I'm going to go ahead and put it all in there by 1,000. Okay, and I should get my answer. Now the question, you guys, comes up about significant figures, and so right here we have 1, 2, 3. Remember, even though this is a trailing zero, there is a decimal that follows it, so there are 3 significant figures. So in this case, it would be, your answer would be 1.8, and this 7 will help the 0 round up, so it would be 1.81 times 10 to the negative 12 meters. So our answer in this case, our answer is 1.81 times 10 to the negative 12 meters. Okay. All right. Okay, so this concludes my lecture on quantum equations. We used wave equation, and we used the Planck's equation to solve our problems. Okay, thank you.